Hi everyone, and welcome to this video poster on second post-Minkowskian scattering from amplitudes in any dimensions. Let me start by thanking the organizers for this nice initiative and for the possibility to keep Cortona alive despite the current situation. In this video, I would like to talk a bit about some recent work done in collaboration with Andrea Cristofoli, Paolo Rigdam-Gor, and Paolo Di Vecchia. So we will consider the problem of black hole scattering in generic dimension B. And let me start by presenting some motivation for studying this problem. So as we all know, recent breakthroughs in the gravitational wave physics, in particular the observation of gravitational waves emitted by black hole and neutron star merger events, has spurred greater interest in the understanding of the physics of the binary problem of two compact objects. And in particular, let me draw your attention on the fact that the physics, in particular the gravitational interaction involved in the very early spiral phase of a black hole merger event, involves gravitational interactions that can be treated perturbatively, so that they are sufficiently weak and they lend themselves to a perturbative study in powers of G, as we will see, the so-called post-Minkowski perturbation theory. So this problem motivates us in understanding better the scattering of two black holes that is due to weak gravitational interaction. So this is the problem that we will consider, and let me also draw your attention on some interesting observables that allow us to gain deeper understanding of this problem. Namely, we like to describe the effective two-body interaction of these two compact objects by an effective interaction potential, long-range interaction potential V. Another interesting property of these two black holes is the relation between momentum and distance along the classical trajectory. And another interesting observable is the deflection angle, so the total deviation that is induced in their trajectories due to their interaction. So as I was mentioning, we will study the problem not in complete generality, but rather we will focus in a regime in which gravitational interaction is weak. It can be regarded as a weak perturbation, or more precisely, this parameter, which is essentially the ratio between the effective Schwarzschild radius of the system and the impact parameter B, is very small. This does not mean, however, that we will consider also a regime of small velocities. In fact, we will be interested also in objects moving at relativistic speeds. And this is actually motivated by the physics of the problem, because in actual black hole merger events, black holes can move very fast compared to the speed of light at, let's say, 0.5 compared to the speed of light. And in particular, we will focus on the 2pm, so the part of this perturbative expansion that is proportional to Gn squared. So a possibility in order to study this kind of problem is to analyze the classical dynamics by studying the Einstein equations and the Worldline equation coupled to one another and perform a perturbative expansion of this classical set of equations. But more recently, it has been proposed that an efficient strategy to study this problem could be to first analyze the quantum scattering amplitude, the one we calculate from quantum field theory, in particular in Einstein gravity, and successively to take the classical limit, which in our case is tantamount to imposing that the separation, the typical separation, for instance, parameterized by the impact parameter B between these two systems, be very large compared to the quantum wavelengths associated to the quantum behavior of the two black holes, so the de Broglie and Compton wavelengths, or in terms of the exchange momentum, that the exchange momentum Q be very small compared to the momentum in the center of mass frame and the masses of these systems. And these are all assumptions that are very well verified in the very early spiral phase of black hole merger events. Let me also mention that we will restrict to the scalar case, so the case of non-spinning black holes, And for simplicity, we will also neglect emitted radiation, which is actually very important for the final applications of this kind of analysis. But for simplicity, let us restrict to the case of an elastic 2-to-2 scattering amplitude. So let us look at this object a bit more in detail. The amplitude, the 2-to-2 amplitude will have, of course, a 3-level part and one loop level part, and so on and so forth, as it is organized already in the perturbative expansion in powers of g. And so we see already that indeed the perturbative expansion of quantum field theory is to some extent tailored to the problem that we are interested in. However, when one studies the semi-classical limit of this amplitude, one finds a number of surprises, a number of puzzling or problematic features, possibly, namely the following. So first, the 3-level part, of course, is associated to classical behavior of the system, and this is something that matches our intuition. And in particular, according to our convention, it consistently scales an overall h bar to the 0. Then there are some one-loop terms that, according to our intuition, also scale as h bar or h bar log of h bar, so they are they can be indeed neglected in the classical limit. However, there are also terms, in particular those arising by from the calculation of triangle and box topologies that are not quantum. In fact, terms coming from triangle topologies are in fact classical, so they are as classical as the 3-level contributions, and an even more puzzling or more surprising feature, contribution coming from box topologies are actually super classical, so they scale in a singular manner with h bar. In particular, they have this 1/h bar behavior. Furthermore, an important point to realize is that box topologies are also responsible for the imaginary part of the amplitude and for the infrared divergence. And in fact, the arising of infrared divergences is also one of the main reasons motivating the fact that we are working in generic D, which allows us to keep under control all possible infrared singular behavior thanks to dimensional regularization. So schematically, the amplitude can be recast in these 3 contributions: a classical one arising from the 3-level, a classical one arising from the 1-loop level, and a super classical one arising from the 1-loop level. And then we will neglect higher order contributions in the Post-Minkowski expansion. Now, how do we derive, for instance, the effective interaction potential that I was mentioning earlier? So the strategy is the following. One considers an effective description of the system in terms of a 2-body dynamics described by a Hamiltonian H of this form, and makes in particular an ansatz for the potential describing the effective interaction, the effective long-range interaction. And we take this ansatz to be momentum space of this form, parameterized in particular by 2 coefficients, C1 and C2. Now, we can also calculate the amplitude associated to the scattering of the 2 objects, the amplitude R, determined by this Hamiltonian. This, according to the standard Born series, will give rise to an expression of this form. So 2 terms proportional to C1 and to C2, and then another term proportional to an integral, and a product of 2 C1 coefficients according to this Lippmann-Schwinger type equation. Now, how do we retrieve finally the potential? Well, we impose that since the effective description and the fundamental or microscopic description provided by Einstein gravity should be equal to each other, they should give rise to the same scattering amplitude up to a factor due to kinematics. So using this matching condition, we obtain a set of equations that allow us in principle to express C1 and C2 in terms of the coefficients appearing in the fundamental amplitude, A3, A classical, and A superclassical. However, we see that there is a puzzle here. So we have three equations for only two unknowns. However, and this is somehow what brings everything together and allows us to perform a consistency check of our analysis. However, the conditions that arise from the superclassical and infrared divergent piece of the two amplitudes are identically satisfied. These conditions are identically satisfied and allow, therefore, to determine uniquely the coefficients C1 and C2 of our ansatz. And finally, to conclude, let me mention that indeed this one loop or 2 p.m. contribution that one finds can be indeed regarded as a small correction in the Postman-Koskian regime due to this form taken by iteration, to the fact that C2 and C1 indeed have a ratio that scales like the center of mass energy. Thank you for your attention.